we want to look at how many different ways we can rearrange these letters right here. Well, we have four spots. I put down 4 dashes. How many choices do you have for that first letter? Well, there you could have an F, an O, an N, or a T, so that's 4 spots. Well, one of the letters has been used, so for your second spot, you only have 3 of the 4 letters left. Now, when we look at our third spot, we used a letter here, we used a letter here, there's only 2 letters left. Well, for your fourth spot, you really don't have any choices. You have 1 spot and you have 1 letter. So we can multiply this together. Now, when it's 4 times 3 times 2 times 1, we could write that as 4 factorial, because factorial means you're starting at that number and multiplying all the natural numbers together below that. If you multiply that out, you get a 12 times a 2, so you get 24. So let's consider this one here. We have now 6 letters, and we want to rearrange these letters into different words. They might be nonsense words or they might be legitimate words, but we want to rearrange them. So we have 6 letters, so we have 6 choices for the first letter. 1 letter is being used there, which means we have 5 choices left over for the second letter. And then we have used 2 of the 6 letters here, so we only have 4 for the next one. And then we continue this pattern. And then 6 on down to 1 for 1 letter for each slot ends up being 6 factorial. So let's consider the word banana. Now, you can think of banana like this, or you can think of it like this here. Now, I did that for a reason, because we have an N here, we have an N here. We have an A here, we have a lowercase a, and we have a Greek A. Well, how many different ways can we rearrange these letters? Well, a total of 6 letters. You put down 6 slots. Just like in the last ones, you have 6 choices for the first letter. 1 letter's been used, so you only have 5 choices for the second letter. Now 2 letters have been used, so you only have 4 for your third letter, and so on. So it ends up being 6 factorial. However, we need to consider what's going on here. We have N's being repeated twice. We have A's being repeated 3 times. So before we finish this problem, we're going to look at a side note. Since A is being repeated 3 times, we need to look at how many different ways could we rearrange the A's. Because if we take an A and switch it with an A, well, that doesn't really change the arrangement of the word, does it? So you need to consider eliminating those choices or options that we put in there initially where A's have been switched with A's, which don't really change the word. So how many different ways could we rearrange these 3 A's? Well, for your first choice, you have 3 different A's you could use. For your second choice, you have only 2 A's left because you used one of them. And then for your third choice, you only have 1. So in other words, it's 3 factorial. Now, another thing you might want to consider, and by the way, when we do this, we get 6, is write out all the different ways you could rearrange these 3 different looking A's. Now, I wrote them as 3 different looking A's, but in the word banana, they're not really different. So, we could have this, or we could have this one here, where we switch the last 2 letters. Well, I could start with lowercase a in front and the other 2 letters behind. Now, I could just switch the last 2 letters. So now I could also start with the Greek letter A, which is alpha in front, and then switch the last 2 letters. So we have then a total of 6 arrangements, which we knew up here. So when we go back here, we're going to still have all this on top that we talked about. Now, since we have an A being repeated 3 times, we need to divide by 3 factorial for A because we had said on this last slide that these three a's could be rearranged in 6 different ways, or 3 factorial. And when we do that, it really doesn't create a new word. And we're looking for all the different unique arrangements or distinguishable arrangements. And so we get a, basically, sorry about that, get rid of all of our duplicates that we have because we have a repeated element. Now you'll notice you also have n showing up. Well, you could have big N followed by little n, or little n followed by big N. So you got to divide by 2. Now, if you look at it like we did with the A's, you'd have 2 n's. How many choices for the first n? 2. How many choices for the second n? Well, one's already been used, so you only have one choice. So that's 2 factorial. Well, if we follow that pattern, we also have a B. So how many? A was being repeated 3 times, so we divided by 3 factorial. N was being divided or repeated twice, so we divided by 2 factorial. So we're going to divide by 1 factorial for the B. Now 1 factorial doesn't change it. Now this is going to come into play a little bit later here. So if we work this out, we're going to have 6 times 2 on the bottom, which if you expand the top and simplify, you're going to be left with this. So we get a total of 60 different unique distinguishable arrangements of these letters. So try to go ahead and do the word parallel. So pause the video, try this one on your own. Well, we have 8 letters. So you have 8 choices for the first letter. 1 letter has been used. 7 choices for the second letter. 2 letters have been used. 3, or so only 6 choices. So in other words, we get 6 factorial. Not 6 factorial, I can't even read here. 8 factorial, sorry about that. But you'll notice we do have some letters being repeated. We have a couple A's showing up. We have 3 of the L's showing up. But then we also have an R and an E and a P. So P shows up once, so we're going to put down 1 factorial. The next letter that we have is A, so we're going to put A down. And that shows up twice, so we're going to divide by 2 factorial. The next unique letter is R, so we're going to divide by 1 factorial because it shows up once. And then we have L, and so we're going to put down 3 factorial because it shows up 3 times. And then we also have an E, so we're going to divide by 1 factorial. So the 1 factorials don't really change it. So it's really just a 6 from this, a 2 from this, so we're dividing by this here. Now I'm not going to go through the arithmetic and expand that any farther. You guys could if you needed to. So consider this situation. We have 29 members of a math club, and they want to elect a president, a vice president, a secretary, a treasurer, and a bailiff. How many ways could they not re-elect, but elect officers? So try this one on your own, and then watch the video. So for the first person you try, you'd have 29 options. For the second person you try, you'd have a lot of options, so 28, and so on. In other words, it ends up being 29 factorial on top, just like it was with those words. So we have 29 factorial. So we have your president. President showing up once. So just like in the last one, when it showed up once, it's 1 factorial. Vice president showed up once, 1 factorial. Same with the secretary and the treasurer and the bailiff. Now, we have 1, 2, 3, 4, 5 items that have been taken out. Well, that means we have 24 items, 24 people. Just like we had 3 L's when we put down 3 factorial. We have 24 people that aren't being used, so we need to get rid of all those, I guess, multiple times they show up. So those are the people that aren't being used, the non-elected members. And sorry, this should be non-elected rather than elected. So in other words, it's 29 factorial over 24 factorial. So how did we get that 24? Total number of people minus the elected positions. Now this happens to be the formula for permutations. If you were taking 29 and selecting 5 at a time, this is what you would do to work it out. And then you get 29 factorial over 24 factorial is one way to do it. Now, it could be done with the dots like we did the very initial problem. And you could write the following. So it could be written like this. If you take 29 factorial over 24 factorial and simplify it down, it would get this. Because you'd have 29 options for the first person. One person's been used, so for the second person it's 28 because there's one was used, 28 left. After the first two people are elected here, just a second here. First two people are elected, two are used, so out of the 29, there's only 27 left for the next person. So you could think of it that way also. But this way also has some advantages to thinking of it. So consider this one here, where we're electing 3 representatives. How many different ways? Well, it's really like the last problem. You'd have 29 people, and then 29 minus 3, because we're only electing 3. The last problem we were electing 5. However, if we elect Bob, Joe, and Jillian, that's the same as if we elect Jillian, Bob, and Joe. So we have our permutation part that we were just dealing with, but it's kind of like that repeated element stuff in a way. We got to divide by how many different ways we could rearrange those 3 people. Because if we have Bob, Jillian, and Joe, if we switch the order of those 3, it doesn't really make for a different representative group. So we got to divide by those repeated ones. So if we have 3 people we're putting on there and we just switch the order, how many different ways can we switch the order of those 3 people? Well, let's see, you'd have 3 options for the first one. One person's there, you'd have 2 options left. Oh, that's that 3 factorial stuff again. So we have to divide by that. So this blue part here is taking all of our permutation stuff that we were doing, and it's dividing by those, I guess, different ways of doing it that end up being repeated. So it's getting rid of all those repeated ones. So it ends up being just 29 factorial over 26 factorial times 3 factorial. Now, if you wanted to work this out, remember 29 factorial is 29 times 28 times 27 times 26 and on down. But isn't this 26 and on down? So it's really just a 28, a 29, a 28, and a 27, because the 26 and on downs cancel out. So 29, 28, 27 over a 3 factorial, which is 6. And then that's all you have to do to work it out. Now this ends up being a combination. And combinations are non-distinguishable elements, meaning they're alike. And like we said, if we take Bob, Joe, and Jillian and rearrange them, it's really the same group. They're all alike.